Hello and welcome to another video. Today we're going to be going through something called ring homomorphisms. Now previously you're used to looking at homomorphisms on sets and operations, whereas today we're going to be looking at a particular case. We're going to be looking at a homomorphism between polynomial functions and rings, which is slightly different. This video is particularly aimed at undergrad students, or let's say level 7 or second year math module takers or algebra takers. So we're going to get straight into it, and the proposition is, we're going to say let R be a subring and alpha is an element of the commutative ring S. Also, this is a little tangent, but this video will be uploaded onto the Telegram and the YouTube, so it will be on both. But previously it was just on the Telegram, now it's going to be on YouTube also. So following the proposition, we have the assumption that R is a subring and alpha is an element of the commutative ring S. Then we give rise to a function, and this will be R going to S, and we'll have the element F map into F alpha. And this is a homomorphism. Now, what is a homomorphism? If you haven't covered it already, I will briefly go through it. So we have two groups. We have G of the operation star, and we have maybe H with the operation star also, and assume they're both groups. Then the function that maps G to H is a homomorphism if and only if f of xy is equal to f of x operated by f of y, and this is for all xy and the elements in the set G. If one of these, this has to be a general principle. If there is one particular case where this doesn't work, then it is not a homomorphism. So we see how delicate this dichotomy is. Now I'm going to go to a new board. So we need to, what should I do? Should I rewrite it? I'll rewrite it. So R is a subring and alpha is an element of S. S is a commutative subring. Sorry, a commutative ring, not subring. Now, let's get on with the proof. Wait, haven't done the function as well. I need to do the function. So we say R subring going to the ring, and F being mapped to F of alpha is a homomorphism. So here we're going to go ahead with the proof. Now with the proof we need to first of all set two polynomial functions to be more precise, and we need to show that they follow the definition of a homomorphism both for multiplicative ordinary notation and ordinary addition. Now I'm going to start with multiplicative. That's much easier, and intuitively we will follow with the additional notation. So the first thing we're going to do in our proof, and it has to be very rigorous, we have to set f equal to the sum, there we go, and our second function is going to be equal to have b x to the j, and let them both be polynomials over R. And R is our subring, not the set of real numbers. Now, then we need to establish that f of g something 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 all the way to the end is equal to phi of f phi of g. So the aim of this proof and the aim of the game is to get from one step all the way to the next without breaking any rules, and properly rigorously defining our axioms as we go. And if we cheat and make one wrong move, then we have an ill-defined proof, and we've used something very wishy-washy, and we've used something that mathematicians shouldn't do. So we have to be very strict. And the first thing I'm going to do is say phi of f and g, and I'm just going to write out what this means by substituting our functions in. I'm not cheating. If I do cheat, I'll call myself out. So here we go. We have n, I starting from 0, and we have m with starting from j is equal to 0, and we're just going to put our functions in like so. We haven't cheated yet so far, and we're not going to cheat. Now, here we are. What I'm going to do now is, by using the simple definition of the sum function, I can say when you times two summations together, you can add their limits together. So here's what I mean. Instead of having n and m, I could do m plus m is equal to, and starting from k0. What is k? K is our dummy variable, and I'm saying from here, k, and I should say it maybe up here, k is equal to I plus j. That's simple as that, and I'm going to have that in here like that. That's simple enough. I haven't made any mistakes. I haven't made anything ill-defined. So here we are, I plus j in our new summation here, and we have ai bj, and then we have the polynomial x to the k. Why is it x to the k? Remember, we had xi over here and we had xj over there, and when you times these two polynomials together, you have to add the power, and it will be x to the I plus j, but I said I plus j is k, therefore I can write x to the power of k. Next, I can also write it like this, k is 0, and I can take it outside, and now what I'm going to do is, the most important part is apply my fixed element alpha. So if I just write this all out, my fixed element now is alpha. Like I said before, alpha is fixed, the functions will vary. This is the difference between ring homomorphisms and the traditional ones. Maybe a first year would see, and maybe a second year. At least a second year would definitely see this as well. But here we go, and we have, sorry, that's not neat enough. And we have a to the I, alpha to the I, and I'm gonna expand it out like so. So to AI and BJ, we're gonna apply the polynomial to the summations. So we have two separate summations now. Again, this is allowed because this follows the property of our function. Now, if we see something and we're particularly sharp in the eye, we can see that this is our function f and this is our function g. And lo and behold, we have reached the end. We have reached phi of f, phi of g. If we look at the steps in between, we haven't cheated, we haven't done anything ill. We've just simply gone from phi of fg, and we've taken it and we've expanded it and we've applied alpha and we've manipulated it. We've just manipulated it just so it looks like phi of f, phi of g. That's the first part of the homomorphism definition. The second part we'll be doing is we'll be looking at the additive notation. So let's get on with that. Now, when we're working with the additive notation, we need to assume one important thing. Like before, we had f being the sum all the way to n and g being the sum all the way to m. We need to assume one thing. If n is greater or equal to m, then we can write this. We can write the following. We yield so we can rewrite this function g as we put before, and we can write it as the sum all the way to n. With b subscript m plus 1 is equal to all the following b's up to bn, and that has to equal 0. Assuming that all those following, not iterations, but all those following terms of b are 0 all the way to bn, then we can shift the value of the sum being to n itself. Why do I need to do that? Because that's particularly important when we're later on adding and manipulating to match the definition, and you'll see it in a second. So the second part of the definition we'll be using is ordinary additive notation. So f plus g. So we have now phi of and that's going to be equal to, and I will tell you what I do afterwards. Okay, all I've done is I've taken out the sum. I've said that the function of g can be written as to the sum of n rather than to the sum to m, because I said bn plus 1 all the way to bn is 0. I've assumed that. Now, after writing it like this, I can apply my fixed alpha. After I apply my fixed alpha, it's quite simple. I can just expand this fixed element and take it out with the summations attached. So here we have Apologies, I made a mistake. If I've assumed the summation is changed, that has to turn to bi. So this will make this bi also. That's a. We have alpha I plus that's what we have so far. And again, if we show that this is equal to phi of f again, and this is equal to phi of g. And again, we've shown that this follows the additive notation. So phi of g. And that completes our proof. Assuming when we apply an element, the element is still in the subring. But there we go. That's the proposition proved. That's what a ring homomorphism is. The next video will be going over roots of polynomials. That's what follows this. But yeah, this will be on the Telegram and maybe YouTube. We'll see. But thank you, and I'll see you next time.